All right, so now we're going to talk about a special class of matrices, and we think about diagonalizing them. So recall that an n by n matrix A is, let's assume that the entries are real. A is symmetric if A transpose is equal to A, right? That's the definition. And we've already noticed that if A is symmetric, then eigenvalues of A are real, so we don't have to worry about arithmetics about complex numbers in this case. That's one thing that we know. Now, another thing that we know is the following. Now, if eigenvectors of, so again, A is symmetric, again, A symmetric, now then eigenvectors of A corresponding to distinct eigenvalues orthogonal. Okay, that's something we can prove. We'll do that now. So suppose we have two eigenvectors. Let's say AU is lambda U, AV is mu V with U and V non-zero vectors, and the lambda not equal to mu eigenvalues. Then here's what we're gonna do. We are interested in showing that they are orthogonal to each other, so we want to consider the dot product. What we're gonna compute is this quantity, U dot AV. Okay. Now this, on the one hand, is, well, AV is mu V, so this is U dot mu V. So that's mu times U dot V. Now on the other hand, you see, there's a formula that we've used before, right? This is the transpose, U dot AV is U transpose times AV. And there's another expression of this quantity that's AV transpose times U, right? You can check that. I mean, we've argued this before, that these two expressions are just equal. But AV transpose U is V transpose A transpose U, right? Now, A is symmetric, so A transpose is A, and you can decide to compute AU first. Now AU is lambda U, so this is V transpose lambda U. That's lambda V transpose U. That's the same as lambda times U dot V, or should I say V dot U. Okay, so what this sequence of equality tells you is that lambda times U dot V is equal to mu times U dot V. So what this means is that lambda minus mu U dot V is 0. Okay. Now since lambda is not equal to mu, lambda minus mu is not 0, we have U dot V equal to 0. That's exactly what we want, because that's the definition of U and V being orthogonal. Okay, so if we are looking for, let's write this down. So if a symmetric is diagonalizable, say D is equal to S inverse AS, then as we discussed before, columns of S are eigenvectors of A. We may expect, because for distinct eigenvalues, the eigenvectors are orthogonal, so we may actually expect that columns of S are pairwise orthogonal. Again, at this point, it's an expectation. But it's a reasonable expectation. And what we're going to do now is to formally consider matrices with that sort of property as follows. In the definition, a real n by n matrix Q is an orthogonal matrix if Q is invertible and Q inverse is Q transpose. Okay. What this condition being invertible and with inverse being Q transpose is the same as saying Q transpose Q is identity. Okay. So that's that. Now it is now immediate to work out the following remark, that if Q is written in columns Q1, Q2, Qn, again these are columns, then here is how we compute, well, here's how we understand the condition of being orthogonal matrix, right? Q transpose, if Q is written in columns, Q transpose is naturally written in rows. The transpose the rows being the transpose of the columns, right? So rows, okay, and now you work out the following computation. Q transpose Q has ij's entry is given as follows. Q transpose Q. Q transpose is written in columns, so it is written in rows, and Q is written in columns. Now, when you try to compute Q transpose Q, what you're doing is you take a row and multiply with a column. And the way matrix multiplication is defined, what you're multiplying turns out to be just, what you're getting turns out to be just the dot product of the column vectors. So the ij's entry of Q transpose Q is just, well, you're taking the i's row from Q transpose, so it is this, dot with, well, not dot with, the matrix multiply with the j's column of Q, and of course this is the dot product Qi dot Qj. And so Q, and now the ij's entry of the identity matrix is what we call delta ij. It's either 0 or 1. It's 0 if I is not equal to j, and it's 1 if I is equal to j. Right? That you know. So Q, having Q transpose Q equal to identity means, or is the same as saying that Qi dot Qj is equal to 0 when I is not j, is equal to 1 when I is j. So, and this condition here about the dot products between the Q's, this is saying that the collection Q1, Q2, Qn is an also normal set. Okay. So that's what we can understand immediately from the definition, that being a matrix Q is orthogonal if and only if its columns form an also normal set. Okay. And yeah, let's look at some examples that are not trivial. Certainly, if you take the identity matrix, you see it's immediately see it's orthogonal. Let's make a more complicated example. Okay, so suppose this is, suppose we consider this matrix, and we want to, if we want to verify whether it's orthogonal or not, we just have to compute Q transpose Q, right? So like that. This is Q transpose Q1 transpose Q1 transpose Q1 is then, well, there's an overall factor of 1/2. Then we do 1. Here is 1, here, there, so that's 2. Here, there, that's a 0. Here, there, that's a 0. Here, there, that's 0. Here, 2. Here, 0. Here, there, 0. Here, there, 0. Of course, here, 2. So this is the identity. Indeed, that's a symmetric matrix. That's an orthogonal matrix. Let's look at another example. So let's say Q2, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0. Okay, this is Q2, and Q2 transpose is 1, 0, 1, 0, 0, 1, 0. Okay, so Q2 transpose is this. Q2 transpose Q2 is then, I'll still have to do it. 1, 0, 0, 0, 1, 1, 0, and 0, 0, 1, which is the identity matrix. Okay, and Q2 is an example of what we call a permutation matrix. Okay, so what is a permutation matrix? It is a matrix obtained from the identity matrix of certain size by permuting columns. Okay. Right. Indeed, if you take the 3 by 3 identity matrix and permute and do the following permutation of columns, let's see, you exchange C1 and C2, that'll give you this one, right? And then you exchange C2 and C3, and that'll give you Q2. Okay. Now, because columns of the identity matrix are also normal, right? The columns of identity matrix are just those vectors E1 through En. They are obviously also normal. Okay, permutation matrices which have columns the same as columns of the identity are also permutation matrices also have columns being also normal. Permutation matrices also have also normal columns, hence are hence are orthogonal matrices. Okay. All right. So now here comes some properties of orthogonal matrices. Okay, so this you have Q n by n orthogonal matrix. Okay, then here are some properties for first one for x in Rn. We have, if you apply Qx, its length is equal to the length of x. 2 for x and y, both in Rn. We have Qx dot Qy equal to x dot y. And 3, determinant of Q is plus minus 1, plus or minus 1. Proof. Okay, so how do we prove this? 1 and 2 are in fact the same thing. So let's prove 2 first. So Qx dot Qy, we want to compute Qx dot Qy, and we know what that is. It's the Qx transpose matrix multiplied with Qy. Oops. Right. Now this is by the property of transpose, x transpose q, y. And you can choose to compute the product in the middle first. But that computation, well, what is it? Q transpose q is by definition the identity matrix. So you just get x transpose y, which is x dot y. That's 2. Now for 1 is exactly the same computation as 2, just because the length square of qx is qx dot qx, which is now x dot x according to what we just proved, which is the length square of x. That's 1. Now, so finally for 3, we can look at determinant of q transpose q. That's the determinant of the identity, because q transpose q is identity. Now the determinant of the identity is 1. On the other hand, determinant of q transpose q is determinant of q transpose times determinant of q. And also, a matrix the transpose of a matrix has the same determinant as the matrix. So determinant of q transpose is determinant of q. So you're looking at determinant of q squared equaling 1. That means the determinant of q is plus or minus 1. Okay. So now we are ready to move on and state the following main theorem here. Suppose A is a n by n matrix with real entries. Now there are 2 parts. Part A. If A is symmetric, then there exists Q orthogonal and D diagonal such that D is Q transpose AQ. In particular, D is, A is diagonalizable. Okay. Now B is sort of the converse statement, which roughly says if A takes this form, then A is symmetric. That is, if D is Q transpose AQ with D diagonal and Q orthogonal, then A is symmetric. So now, unfortunately, the proof of A is complicated, so we're only going to state it without proving it. The main point of A is, of course, if A is symmetric, then it is diagonalizable with the particular form. That is the matrix, the eigenvalues, not the eigenvalues, the eigenvectors can form an orthonormal set. Now for B is just a check, right? So how do we do this? D is equal, we are saying that A has this property that D equals to Q transpose AQ, but that implies A is equal to Q transpose inverse D Q inverse. That's A. Okay. You see Q transpose is Q inverse because Q is orthogonal. So this expression is the same as Q inverse twice, so that's Q D Q transpose equaling A. Okay, so when you have this expression for A, you can now try to use it, QD Q transpose, take the transpose of this expression to get A transpose. We do that. And the property of transpose tells us that we are looking at this expression. Now, transposing twice gives you back, so you have Q for the first term. Now D is diagonal, so its transpose is equal to itself. And then lastly is still Q transpose, but this is A, right? So that proves that A is symmetric. Okay, so now remark by theorem part A is symmetric. If A is symmetric, then A is symmetric, then you can write D equals A Q transpose AQ, where Q columns of Q are eigenvectors of A. Q are eigenvectors vectors of A. Now, because Q is orthogonal, right? That was the statement we made. The columns of Q are, what are they? Are in, well, should I say they form, columns of Q form a set of n also normal vectors. In where? In Rn. So what this is an also normal basis of Rn consisting of eigenvectors. Okay, so that's what we can do. If you have a symmetric matrix with real entries, you're guaranteed by some theorem that we didn't prove that is diagonalizable. And in fact, you can find a basis of Rn consisting of also, you can find also normal basis consisting of eigenvectors. Okay, so now let's look at some example. Yes. So let's see here. Example. So this is a somewhat bigger one. 1 minus 1 minus 1 minus 1. 1 minus 1 1 minus 1 minus 1 minus 1 minus 1 1 minus 1 minus 1 minus 1 minus 1 1. There's a lot of minus ones, but you can see certainly that A is symmetric. Okay, so according to the general discussion we just made, it's supposed to be diagonalizable, and we are supposed to be able to find an also normal basis of R4 consisting of eigenvectors of A. Let's try to do that. Okay, so the first step, as usual, is to compute the compute the characteristic polynomial. Okay, so there's that. Okay, and maybe there's some easier way to do this. Yeah, so we can try to simplify the computation before we proceed, right? The question is whether it was doing that or not. Well, we can try. Here's what we're gonna do. We will, well, we will not. Let's just do it the old-fashioned way. Okay, so that's first, we're expanding along the first column. So that's the first thing. And minus -1. Minus 1 minus 1 minus 1. Minus 1, 1 minus t, minus 1, minus 1 minus 1, 1 minus t. Plus minus 1, minus 1, minus 1, minus 1. Let's see here. 1 minus t, minus 1, minus 1. Minus 1, minus 1, 1 minus t. Minus, minus 1. Minus 1, minus 1, minus 1. 1 minus t. God, that's going to take a while. Minus 1, minus 1. Hold on, yeah, right. Minus 1, 1 minus t, minus 1. Okay, yeah, that's going to take a while. So we be patient and try to do it. Probably should do things on the side. This guy 1 minus t, minus 1, minus 1, minus 1, 1 minus t, minus 1, minus 1, minus 1, 1 minus t. This guy is equal to, again, first column expansion, 1 minus t, minus t, minus 1, minus 1, 1 minus t, minus, minus 1, minus 1, minus 1, minus 1, 1 minus t, plus minus 1, minus 1, minus 1, 1 minus t, minus 1. You see? Yeah, well, let's do this computation. So this is 1 minus t, 1 minus t squared, minus 1. So t squared minus 2t plus 1 minus 1. So t squared minus 2t. Now over here I have plus t minus 1 minus 1. And I have minus, what is this, 1 plus 1 minus t. Is that right? Minus 1. Yeah, that's right. Minus 1. 1 plus t minus 1 minus t. Yeah. So this is t minus 2 here, minus 2 minus t. So t 2t. So t minus 2 minus minus 2 plus t. So 2t minus 4. 1 minus t. T squared minus 2t plus 2t. 2t minus 4. We're going to factor this now. So 1 minus t, t squared, t minus 2 plus 2 t minus 2. So it's t minus 2. What is it? T minus what is it? 2 plus t minus t squared. Okay, that's the first bit. It's a lot of computation. And maybe we are, yeah, well, let's, I don't know, let's see how patient are we. Well, let's see, is there anyone that's slightly easier to do? Maybe we'll do let's do one more and leave out the rest for whoever is watching this. So again, we're going to expand along the first column. That's 1 minus t, minus 1 minus 1, 1 minus t, minus 1, minus 1 minus 1 minus 1, 1 minus t, plus minus 1, minus 1 minus 1, oops, minus 1 minus 1, 1 minus t minus 1. So we're getting minus 1, 1 minus t square minus 1. So that's again is t square minus 2t plus, what is this? T minus 1 minus 1, t minus 2 minus 1 plus t minus 1 minus t, so 2 minus t. So seems like we can factor out t minus 2 again. So it's a minus t out here for the first term, and plus, no, it should be a 2, yeah. Right, so it's 1, yeah, that's a 2. Okay, like that. Well, then there are certain 2 other things to compute, but if you actually do all of them, you will get that the determinant of A minus Ti is equal to, and this is because of the fact that we've been factoring out T minus 2 in the process of the computation. You get that. So from here you get eigenvalues to be 2 and minus 2. The algebraic multiplicity for 2 is 3, because you see T minus 2 has 3 factors occurring in the characteristic polynomial. And for the minus 2, the algebraic multiplicity is 1. So now we are ready to solve the system. Sorry, solve for eigenvectors. Let's begin with the easy one. For lambda equal to minus 2, the system we need to study is ax equal to minus 2x, or 3 minus 1 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 minus 1 3. This system equal to the 0 vector. Okay, and you kind of see immediately there's one solution. If you take the x's to be all 1, then the equation is true, right? And we know that it can only be, the eigenspace is one-dimensional because the algebraic multiplicity is 1. The geometric multiplicity has to be 1. We know the eigenspace is one-dimensional, so these are all the solutions. or a multiple of this vector is all the solutions. So let's call this guy so we're gonna say W4 is this vector. Now we deal with the lambda equals to 2 case. The system is AX equals to 2X, or in other words, minus 1, minus 1, minus 1, minus 1. It's minus 1 everywhere. With 4 unknowns. Now all 4 equations are the same. Right? You know how to, you can certainly, there's nothing really you need to do, right? The equation is the sum of the 4 variables to equal to 0. And that basically means you can find, that basically means you have 3 free variables and 1 dependent variable. So you have a 3-dimensional space of eigenvectors for this eigenvalue. Say, I don't know. Let's think about this. So, say x1 is still x1, x2 is still x2, x3 is still x3, and x4 is minus x1 minus x2 minus x3. Okay. And this is x1, 0, 0 minus x1 plus 0, x2, 0 minus x2 plus 0, 0, x3 minus x3. So this is x1 multiple of 1, 0, 0 minus 1, x2 multiple of 0, 1, 0 minus 1, x3 multiple of 0, 0, 1 minus 1. Okay. All right. So we found 3 vectors. Say, I don't know, call them W1. This one, 1, 0, 0 minus 1. W2, 0, 0, 1, 0 minus 1. W3, 0, 0, 1 minus 1. Right? So these are certainly eigenvectors with eigenvalue 2. And you can check immediately that they're linearly independent. Now, the thing is they're not also normal, right? Certainly, even with W4, they're still not also normal. For the discussion, according to the discussion we made before, we should be able to make them also normal. It is clear that W4 is orthogonal to W1, W2, and W3. So we just have to make W1, W2, W3 into also normal bases, right? That we can do. That we should run Grand-Schmidt to get orthogonal bases first. So let's say U1 is W1, right? Now U2 should be obtained from W2 by subtracting some direction in U1. And that's the direction. So W2 is 0, 1, 0 minus 1. minus, what is this number? U1 dot with itself is 2. W2 dot WU1 is a 1. So this is 0, negative a half, 1, 0, minus 1, minus negative a half, so plus a half, negative a half. Okay, yeah. Now, finally, U3 is W3 minus some factor in U1 and some factor in U2. U1 dot U1, W3 dot U1, U2 dot U2, W3 dot U2, and that is 0, 0, 1, minus 1. This is 1, 0, 0, minus 1, minus U2 being this complicated gadget, minus a half, 1, 0, minus a half. Now what are these numbers? U1 dot U1 is still 2. W3 dot U1 is again a 1. U2 dot U2 is complicated now. So quarter, another quarter, a half, so 3 half. Now W3 dot U2 is not too bad. So just a half. Okay, so this is just 0, 0. Maybe I should write it out first. 0 minus a half. So this cancels. This here cancels to a third. This is 1/3. Okay, so minus a half minus plus a 6. And it's 0 minus 0 minus a third. Okay, and it's 1 minus 0 minus 0, and the minus 1 minus, well, negative a half, so plus a half, minus plus a third, a 6. Okay, so this is again some complicated thing. Minus a third, minus a third. 1. Is minus a half plus a third, a 6. So minus a third. Okay, so we now, what we've done here is we've applied the Grand-Schmidt process to obtain from the W1, W3, 3 new vectors that are now orthogonal to each other. Together with W4, you now get orthogonal, a collection of 4 orthogonal vectors, and you have to normalize them to make them also normal. That's just going to get a bit tedious, so we will not write it out. But this is in principle how you do it. When you have a symmetric matrix, you proceed to compute, you proceed to solve the eigenvalue problem, which may be complicated at times. But once it's done, once it's done, you may need to run the Grand-Schmidt process and normalization to get to reduce to get to also normal basis. But that's how it's done. All right, that's the end of lecture.